So we've been talking about the fact that the integral gives us the area under a curve, but I want to expand on this and apply it a little bit further than what we've done so far. Okay? We're talking about the area under the curve, and it says here, the definite integral of f of x from a to b gives the area bounded by the curve of f of x, the x-axis, and the lines x equals a and x equals b. Okay, so for example, and it is helpful to sketch these, if we are asked to find the area of the region enclosed by this parabola, x squared plus 1, the x-axis, x equals 1 and x equals 2, all right, we have here a line x equals 1, another line x equals 2, here's our x-axis, and here is the curve. So we're trying to find this area contained within this region, okay? So that's the area we're trying to find. In order to do that, we have to then take the integral from 1 to 2 of x squared plus 1 dx. Okay? So again, we related it kind of visually and theoretically to area yesterday. Now we're trying to make some more concrete applications straight to area. Notice we're getting into chapter 19 right now. Chapter 19 takes us away from just the mathematics of the integral to the application of the integral. Okay? So here we're finding our area, and we can actually calculate this. What's the integral of x squared plus 1? Come on, we know this.
The integral of x squared plus 1?
Yes.
3x over 2? No.
1/2x.
Oh my god. Okay. One of them is 1x. It's plus 1x.
Okay, good. We plus 1x.
And then I put 1 in it, but you do 1/2, you do x cubed, right? Because you do 1 more, and then over the new one.
Over
The reciprocal of the new one.
3. Okay, good. X cubed over 3. Add 1 to the exponent, divide by the new exponent. All right, we can't be that rusty, guys. It's only been a week. Okay? If we're that rusty, you guys need to get on the ball here. Okay? So we've got x cubed over 3 plus x. Now, fundamental theorem of calculus, we're going to evaluate that from 1 to 2. So, this evaluated at 2, we have 8 over 3 plus 2, minus this evaluated at 1. That's 1 over 3 plus 1.
Oh, I didn't know it was small.
So you did 1 over 3, oh yeah.
Okay? It's f of b minus f of a. Remember our fundamental theorem of calculus. So we evaluate it at the top bound, then we subtract it, evaluate it at the bottom bound. So this right here is 8/3, sorry, is 2 2/3. So this is 4 2/3 minus 1 1/3. So that's 3 1/3. Okay? So that's our area contained in that little region there.
How is this any different from what we've been doing before?
Right now, it's not. Okay? However, the applications start and some of the connections we have to make can be challenging. So let's look at one here. Okay? It says find the area contained enclosed by one arch of the curve y equals sine of 2x and the x-axis. Okay? Now, notice we're not given an interval. We're told what part we want, and we've got to figure out the interval. Okay? So let's think this through here. what do we know about the graph of sine of x?
It's like a sine wave, it's like,
Okay, it's a sine wave. What is that? We go,
yeah.
all right. So what do we know about that wave?
Is its period pi or 2 pi?
The normal period is 2 pi, right?
But because it's sine of 2x, it's 4.
So the interval could be from 0 to pi.
Hang on, what is one arch of this? This is just sine of x,
Oh, it's
would be from 0 to pi. However, we have sine of 2x. What does that do to our period?
It expands it, huh?
Shortens it. Because it makes it like, well, just like, ends it out.
Does it shorten it or does it expand it?
Doesn't expand it horizontally.
It's horizontal.
Vertically.
Vertical expansion.
Does it compress?
Let's think.
Isn't that like if it's 40x, then it's a stretch, no?
Oh, it.
Like if you have a plus something, it's a shift. But if you have it right in front of the x, it's
Okay, plus or minus something is a shift.
So before the x is
But-
stretch.
Well, here's the thing. It could be a stretch. The key is stretching and shrinking. We're multiplying by something. The key, though, is where are we multiplying it? All right? Let's put phones away and focus here, please.
Wouldn't it be a stretch, and if you wouldn't one arm take would be 2 pi?
Okay? Look. We're multiplying the x by something. To stretch it vertically, we would be multiplying the whole function by something. That would stretch it vertically.
So it is horizontal.
It is horizontal. However, remember that the horizontal has an inverse relationship. So when you see it x times 2, it shrinks it horizontally. Okay?
Why? Why would it shrink it?
Because, think about it, you're doubling the x coordinates. That means whatever's gonna happen is gonna happen twice as fast. Okay? So it's gonna take half as much space. So, instead of having the graph go up and come down here at pi and then finish off a full period at 2 pi, we have it completing a whole period in just pi units. Which means that first arch ends at pi over 2. Okay? Usually our sine curve looks like this. This one had its period cut in half. So we're going to go from 0 to pi over 2. All right? Listen, these are the kinds of connections to previous knowledge that we've got to be able to make. All right? When you're doing your own practice, if you don't remember, go back and look it up. All right? These are connections you've got to be able to make to things we've done in the past. All right? So, we are taking the integral of sine of 2x from 0 to pi over 2. Now,
So we have to determine our own period.
you
We
got
have
to,
determine our own like area.
yes, you got to determine the interval here that you're using based on what you're being asked to do. One arch of the curve. Well,
That's why we found the period.
yeah, we had to know what the period was because one arch of the curve was half of that period.
Yeah, but you could do the you could do pi to pi if you wanted to.
Well, if we did pi over 2 to pi, what would that area we got? We'd get a negative. Now, if you just understood it was the same and made it positive, you'd get the right answer. Okay? But let's look at this here, okay? We have sine of 2x. What's the integral of sine of 2x?
2 negative cosine.
Hang on, what did you say?
Is that where you do the, what's it called? We take the derivative of the inside.
Okay, we are going to do the derivative of the inside, which is a constant, so it's 2.
2 times negative cosine.
Close.
Close enough.
1 over 2, okay? So, 1 over 2 times the negative cosine, or negative 1/2 cosine of what?
X, 2x.
Of the 2x. That part stays the same. Okay? So, just to recap, the outer function, so to speak, here is the sine. The integral of sine is negative cosine. The inside stays the same. This is a linear function, so it's just times 1 over the derivative. The derivative is 2, so it's times 1 over 2. Alright? Is everyone with us on that? You guys were doing really, really great on this a week ago. Alright, so should be remembering slowly. Okay, so now we have our integral. We've got to evaluate it from 0 to pi over 2. And again, here's where some trig comes in. I would not be surprised to see a problem like this on a non-calculator part of the exam. Okay? Because there's nothing on here that requires use of a calculator. We have here negative 1/2 cosine of 2 times pi over 2. So that's just cosine of pi. Minus a negative 1/2 cosine of 2 times 0. So just cosine of 0. And here's where you got to know your unit circle. What's the cosine of pi? It's on your left. No.
Negative
Negative 1.
root 3 of root
Negative 1.
Negative 1. Negative 1. Okay? Plus 1/2. What's the cosine of 0? 1. Okay? So, negative 1/2 times negative 1 is 1/2. 1/2 plus 1/2. The area is 1. Okay? So that area right there is 1. Now, let's take this a little step further, okay? What if, instead of just one arch, they said find the area contained in one period?
Same thing.
In this case, the integral from 0 to pi of sine of 2x.
Wait, why? I thought the period,
Would it be 0?
I don't understand what the difference between the period and one curve. So how did you know what the first curve was?
Because it was just the arch. Like one.
Yeah, but how did you know that it was pi over 2?
We went through that whole thing here. Normally we have sine is 2 pi, but because of the 2x,
No, I know.
it's
what
cut in
the
half. So
period-
that's how we know it was pi over 2.
Okay.
Alright? The whole period would be crammed into pi, so that half that normally was at pi is now at pi over 2.
But the first curve is always half.
Okay? Yeah, the first curve is half, and
Okay.
yeah, we have symmetry here. So here, let's think about it. If the area of this is 1, what's the area of this side? Negative 1. So what's the area of this whole thing? 0. Okay? If we take the integral from 0 to pi of sine of 2x, we're going to get 0. And that's because doing a definite integral gives us what's called the net area. Net area. Okay? Now what that means is that you have some positive area, you have some negative area, and we just want the positive minus the negative, okay? And some of it's going to cancel itself out. It's kind of like if you get a paycheck, you have your gross pay you get your taxes taken out, that's subtracted, and then what you have left over is the net pay, and that's the money you actually end up getting. Okay? Well, here we have this amount. Some of it was canceled out. In this case, all of it was canceled out, so our net result is 0 area. Okay? Now, let's say that we don't want that to happen. We want the total area instead. The total area contained between the x-axis and the curve. Notice I said between, not under the curve. Okay? If I want the area between the x-axis and the curve, I need to force this area to be positive. So I've got to do two things. Number one, I've got to break up my integral. I've got to break it up to go from 0 to pi over 2. And then I have to also look at the integral from pi over 2 to pi. Okay? So pi over 2 to pi of sine of 2x dx. However, how do I force that to be positive?
Absolute value.
Okay? There's two ways. We could either, because we know it's going to be negative already, we could put a minus in here and subtract that area. Okay, so minus a negative makes it positive, and now we're all good. Or the other option here is absolute value. Okay? So that will force that area to be positive. And what is my answer actually going to be in this case then? 2. The total area contained between the function and the x-axis is different than the area under the curve. Okay? Under a curve, this is above the curve, so that's why it's negative. All right? If we're talking about between the x-axis and our curve, then all of the area will be considered to be positive. Okay? So, we're going to actually see in the second part of the lesson later today why that happens. Okay? And actually another way of getting to that result. Okay? But we'll pick up from that later. Now, our assignment for Thursday, here's what we've got. Okay? There's two problems from page 478. Okay? If you just look up the PDF in the notes section on our class website, you'll see this. You'll see the ones I want you to do. Okay? 2, B, E, F, G, and I. Alright? These ones you're doing by hand. Find the exact value. That means leave radicals as radicals. If there's trig, like in B, use your unit circle. Okay? I don't want to see decimals that are being rounded and stuff. Okay? Find the exact value. If you happen to have a logarithm, leave it as a log and don't plug it in. Okay? Find the exact value of the area of the region bounded by each of the things here. Okay? And then number 4 is really a connection to yesterday. Alright? You're interpreting the problem to write the integral down, but once you do that, then you can just use your calculator to find what the answer is. Okay? So I should see something like this right here, but then you'll just put equals whatever the answer happens to be. Okay? So you've got to figure out what integral you're finding. The calculator can do the hard work because these cannot be found by hand without using some long summation method. Okay? Which we're not going to mess with. Now, another thing. This will be a grade. Okay? This is a summative. It's basically kind of an open notes, open book quiz. Alright? You may not work together on this. you need to work on your own, using your notes, using your book. If you haven't taken notes, then you got your book, all right? But this will be due on Thursday. Show all your work. Show you're using the fundamental theorem of calculus, all right? So, I'm going to give you some time here, the next 25 minutes to start on this, and then we're going to look at the other part of our lesson after that.